All right, let's give everyone just a few seconds to kind of drop on in. Just kind of like make an announcement. Hey, like, Tech Art Talk is live. Watch out. Give everyone just a few moments to drop in. All right, I think we are ready to rock and roll. Hopefully, we'll be able to control the technical difficulties today. But then, of course, what is Tech Art Talk Live without technical difficulties? Aha! All right, well, let's get this show on the road. Greetings, Tech Art students, Tech Art fans from around the world. It is Friday, it is 12:30, and that means it is time for another episode of Tech Art Talk Live. My name is Chris, and I will be your host for today. Now, last week we embarked on a groovy venture of exploring all of what normal mapping could do. And we're going to kind of like deal with normal mapping's kind of like evil twin brother. And I'm not going to say it's evil twin because really kind of like normal mapping, well, needless to say, it's not really evil, but it's just kind of like a brother or maybe a sister. But we're going to deal with displacement mapping. Now, what is displacement mapping? Well, displacement mapping is a little bit different from normal mapping, but the two often get confused. So what we're going to do is go over what normal mapping is today, and then we're going to give a quick example of how to do normal mapping, and we're going to then finish up by going over some of the differences between normal mapping and displacement mapping, because it's good to know when to use which and which are better than others at doing particular visual effects with. All right, so let's get this lecture all started. The lecture of what displacement mapping is now. So last week we introduced the concept of normal mapping. Now normal mapping is pretty cool. We created this evil eye and we had this pillow shape, and here's our normal map, and then what we did was we projected this pillow shape onto the surface, and then we transformed the surface to be in something called tangent space. And so it got the geometry into the exact same location as this texture map, and so it modified the normals to kind of like give us this kind of different look here. And so here we go, and so notice that it displaces the normals and it displaces the specular component just right as if they were smaller little units. But notice here that when we tilt this onto a side, the effect kind of falls apart, and that's because we're losing all silhouette. We aren't really displacing any of the normals, and there's really no geometry, so it's actually flat. So that is one of the drawbacks of working with normal mapping. Okay, so let's go over the normal map. Now I want to first start off with the common vx.h. Now this is the common file that we are including on the little program that we're using in Shader Tool, and where you have a couple of pound defines up above. And what this does is it prevents any kind of global variables or global concepts for being introduced more than once. And so notice that it says if not defined common fxh, then go ahead then define it. And then this right here, there's another pound end if, and what this does is it kind of like bookends all of the stuff. So everything from the define to the end is going to be included into this definition of what common fxh is, and so therefore don't ever try to overwrite it again. And inside of that we've got a little command, say flip texture y, and because this is Shader Tool definitely wants to flip the HLSL textures, and so we're going to say yes to that. And then we have a utility function that is called get corrected texture coordinates that actually does the flipping for us. And then we've got two little helper functions called get vector color contribution and get scalar color contribution. And so therefore, we're going to be given a float 4 light. And then what we're going to do is either we're going to get the color from that light either from a float 3, and that's going to return us the color, or we're going to get the color from the object and we're just going to send it a single float. And those are going to be used for either grabbing the ambient light, the diffuse light, or the specular light. All right, so let's go back to the shader tool here, and let's go over all that's going on here. So let's go take a look at the map itself. Okay, here in the first line, we're going to call the include common.fxh. We just went through the common.fxh, and so that is going to load in the global functions. Now, we're going to want, for constants, we're going to want a content buffer per frame. So that means for all of the objects, and then for all the objects, we want them to share the ambient color, the light direction, the camera position, the camera view, and the camera projection. Yeah, lots of stuff. All right, now remember that the camera view and camera projection are not vectors, they are actually matrices. Those are 4x4 matrices filled with lots of good stuff. Now for every single object in the scene, we're going to have to create a C buffer per object. And for every object, we're going to want a specular color and we're going to want a specular power. Remember, the specular color provides what the color of the specular component is, and the specular power defines on how sharp it is or how diffused over the surface it is. The larger the number, the sharper it's going to be, the smaller it's going to look, but it's going to look a little bit brighter. And the smaller the number is, the larger, more spread out the diffuse, the specular component is going to be, and it's going to look a little bit softer. It's going to look a little less bright. All right, let's go over our input structures. Our vertex shader input, we're going to be inputting our object position and our texture coordinates, and we're going to be importing our normal and our tangent. Now output, coming out of the vertex shader, we're going to be outputting the position, the normal, the tangent, the binormal, and the texture coordinate, as well as the light direction and the view direction. Now remember, on the surface, every single surface has a normal associated with it. And we're also going to create something called a binormal, which is kind of perpendicular to the normal, and it flows around the U direction of the polygon. And the binormal is also perpendicular to the normal, and it flows around the V direction. So we've got the U direction, which is our tangent vector, and our V direction, which is established by our binormal. And then we have our standard shader setup things. And then for this, what we wanted to do is include a color texture, and we wanted a normal map. So these are going to come in, and we're going to define our color sampler, and that is going to be applying a filter to our texture map, and we're going to do the minification, the magnification, and the mipping. Do that all linearly. All right, and then when we do any kind of our U and V space, once they go between 0 and 1 or go beyond that, then we want to use the wrap mode. All right, very simply, so in the vertex shader, all we're going to do is we're going to take our position and put it into world view projection space by multiplying it by the world view projection matrices. Then we're going to get our texture coordinate, and then we're going to get our texture coordinate by applying it to the flipping function, whether we want it flipped or not. Then we're going to take our normal, and then we want the normal to be in world space. And we want our tangent to be in world space too. And so now, since we didn't include the binormal along with that information, we're going to calculate our binormal by taking the cross product of the normal versus the tangent, and that's going to produce our binormal. And then we're going to take we're going to normalize our light direction by just taking the light direction as it was given to us, and we're going to take the negative value of that. And therefore, what we're going to do is get the world position, and we're going to put the world position. We're going to take our object position and put it in world space by multiplying by the world matrix, and then we're going to get our final view direction, which is the camera position minus the world position. And then once we got the result of that, we're going to normalize that. And once again, normalizing is making sure that that vector has a magnitude of 1. Okay, now we're going to take that into the pixel shader. And now the pixel shader has a lot to do, because what it's got to do first is it's going to take the normal, and then it's going to, what it's going to do is it's going to get the normal. It's not going to use the normal as it was given to us from the vertex shader. It's going to get the new normal from the normal texture map. And by doing that, we're going to take the color sampler, and we're going to use our texture coordinates to get its UV position. And then when it's gotten, then we are going to double it. We're going to multiply it by 2 and then subtract by 1. And so what that does is it transforms it from being a vector, going from -1 to 1, into a actual color, which goes somewhere between 0 and 1 instead. And then from that, we're going to take our inputted tangent, binormal, and normal vectors, and we're going to smush them together to create one big matrix. And then we're going to take our sampled normal from our, then we're going to take this sampled normal, and then what we're going to do is we're going to multiply our sampled normal by our TBN matrix. And that's going to put us right into the proper space. And then we're going to take our new normal, which is going to be that sampled normal, and then we're going to normalize that. We're going to normalize our light direction and our view direction. And with that information, we're going to use that to calculate the essential information we need for our diffuse lighting and our specular lighting. For the diffuse lighting, we're going to need to take the normal dotted with the light direction. And then for the specular, what we're going to have to do is first calculate the half vector, which is our light direction plus our view direction. And then we're going to take the dot product between our normal and our half vector, and that's going to give us the proper angle needed for our specular component. And then we're going to grab our color from the color texture map, and then we're going to use the lit function from the HLSL library. And with that, we're going to send it the n.l and the n.h. And then we're also going to send it the specular power, and that's going to return the light coefficients. And then we're going to use those little friendly helper functions that we introduced earlier, and that's going to give us the ambient light, the diffuse light, and the specular. We're going to add all of those together, and voila. What we have here is the normal map as demonstrated. Okay. Lots of stuff going on here. It's really not too difficult. It takes a lot longer to talk about it than to actually show it. All right, so let's go on and actually take a look at what displacement right. So let's go ahead and make the modifications that we need to do this. Okay, first what we're going to do is, as mentioned before, we are going to add the displacement scale to our object. So we're going to go on here, and here we go. We're going to get a displacement scale. So we're going to say float displacement scale. Okay, now notice when I save this, we get a new parameter down here, a new floating variable. So we're going to have to create a displacement scale. So let's go ahead and create a slider down here. And types, we're going to go to slider here, and we're going to go between 0 and 2, because it doesn't take too much to actually displace this thing beyond all recognition. So we're going to go with 2, and then we're going to set the default displacement at 0. And then we're going to pipe that right into the displacement scale. Okay. Now, what we're going to do next is we are going to modify our shader here in order to take into consideration what we have to do for that. And the first thing we have to do beyond creating a displacement scale for our object is we're going to create a new displacement map. So let's go ahead and create a new texture map for our object. And so we have a color map and a new normal map, and so we're going to use is a displacement map. And that's also going to come in as a texture 2D. So let's go ahead and save that. And you'll notice that yet another parameter just popped up there. So it wants another texture map. So let's go ahead and add a displacement map. Okay, so we have our new texture here. We have a little room. Let's stick it in there. And let's go up into here, displacement mapping, textures. Okay, so let's just grab this, let's just grab this simple checkerboard. You know, it's very simple, it's very contrasty. It's got white and it's got black. Wherever you see white, that's where the displacement's going to happen. Wherever you see black, nothing is going to happen. So let's pop that into the displacement. All right, let's continue along our way. So let's go ahead and then modify our structures. Well, you know what? We don't have to really make any modifications. In fact, what we have to do is simplify this. And in order to simplify it, what I'm going to do is I'm going to create a duplicate of both of these. And I'm going to give them some separate names. So I'm going to call it VSD for vertex displacement input and VSD output for vertex displacement output. And for that, we don't need the tangent vector. Nope, don't need them no more. And then we don't need, for our output, we don't need the binormal and the tangent vector either. So this is kind of a reduction and kind of like going to simplify things back to the way that they were. Okay, now I'm not going to overwrite my old vertex shader. My old vertex shader is good, and what I want to do is I want to have two different techniques going on here. I want to have one for normal mapping and one for displacement mapping. So I'm going to go ahead and copy my normal vertex shader, and I'm going to paste this down here, and I'm going to call this instead normal vertex shader. I'm going to call it displacement vertex shader. Displacement vertex shader. And remember, we changed the names that we wanted here. So instead of just a VS output, I'm going to want a VSD output. And for the input, I want a VSD input. And likewise, I got to change that here. And make one more change there. Okay, so what we've done is we have effectively converted our normal vertex shader over to our displacement vertex shader. Okay, and so let's go ahead and make our modifications. We don't really need to do all that much. So here, all this stuff about the tangents and the binormals and all that stuff, get rid of it all. Don't need it. Okay, but the one thing we have to do is we do have to deal with our displacement scale. And so we do have our displacement scale. Okay, so what I'm going to do here is I'm going to go ahead and drop all that in here. And so we have our texture coordinate coming in there. Oh yeah, what we have to do is, let's get our displacement amount from our texture coordinate. So here we go. We're going to grab that information. So let's grab, we're going to go ahead and modify this and move it just a bit. I'm going to move that to the top of the shader. All right, we've got that set. Now let's go ahead and worry about our displacement scale. Now remember, our displacement scale is something that we can control and control how much we displace our object by. I'm going to grab this, and then we're going to put that right underneath there. Okay, so logically, we're going to check the displacement scale. If the displacement scale is greater than 0, that means that if it's 0, don't do anything. But if it's greater than 0, what we're going to do is we are going to go and use those texture coordinates, and what we're going to do is we're going to look at the displacement map. And notice here that once we've gotten the displacement map, yeah, it's going to come in as a red, green, and blue channel. But notice here that we're going to only grab the X component. And because it's basically a black and white image, it's got levels of gray scale in it. So therefore, the X, Y, and Z values are all the same, or the U, X, or the R, G, and B values are all the same. So therefore, we're only going to send that to a float. And therefore, here's our function. Because we're creating an outie, what we're going to do is say the in.objectPosition X, Y, Z equals, plus equals, meaning that we're going to add it to itself. We're going to the in normal multiplied by our displacement scale multiplied by our displacement, which is coming from our texture map. Okay, so now this statement here actually moves our vertex for us. So that pretty much does all of the work for us. And so that what we have there, and so that pretty much does all that. So what we have to do now is make sure that we have our out position, and we need to make a modification to our output position because we've gone ahead and radically changed it all that. So let's make sure that our new object position is within the world projection space. So actually, we're going to leave that right in there, right there, because although the object position has been offset, it's been still in local space. Yeah, it's still in its object space. So what we have to do is make sure that it's in worldview projection space. So we're going to multiply it there, and we're going to leave it there. We are going to take our normal map and make sure that that is our normal. And we're going to make sure that the normal's in world space. We've got our light position and then our world position, so everything is going to be basically the same. And so the only thing that we're missing is the texture coordinate. And we have to pass our texture coordinate on to our towards the shader. So are we, do we have the actual output information? We've got the position, normal, texture coordinate, yep. So what we have to do is update that. And so I'm going to sneak that right in here and say out.texture coordinate is there. Okay, I'm going to say this to make sure I don't have, trilinear sampler. I haven't defined that. Aha, so what we're talking about here is we're going to use the color sampler. So we're not going to be using something on here. This is some old notes that I have. So I'm going to change this to the word color. And then here we go with the texture coordinate in line 105. And this is the texture coordinates. Out.texture coordinate. Oh, you know what? This is my bad. This should be float 2. And it should be the texture coordinates of that. And so that's where that texture coordinate is coming from. I cast that off in the wrong direction. All right, gang. Believe it or not, that was most of the work that we're going to do. So let's go ahead and make modifications to our pixel shader. I'm going to make duplicates of that again, so I have the difference between my normal pixel shader and my displacement pixel shader. And all I'm going to do is get rid of most of the normal mapping stuff, because we don't need to do all that. So I'm going to make this displacement pixel shader, and then we want the VSD output coming in, and that should be good. And so what we have to do for this is we have our out, and then we have our, we don't have to worry about any of this stuff. So get rid of it all. Okay, this is going to make things simpler, but our normal is still going to be the normalization. We've got our light direction, our view direction, our n.l, our half vector, our n.h, and so everything else is the same. So really all that we're doing is removing that, our sample normal, I forgot we have to change that to n.normal, because we're getting it in from the vertex shader. N.normal, and is that going to be right? All right, so no complaints. Okay, now remember how I said that we wanted to create a difference between our normal shader and our displacement shader, but you're probably asking, well, how are you going to do that? Because you're all working in the same file. Well, that's something that traditional HLSL will allot to us. So I'm going to go over here to the part where it says the technique. I'm going to duplicate my technique, and instead of normal mapping, I'm going to call it displacement mapping. All right, and now for the normal vertex shader, I'm going to just go call it the displacement normal map, the vertex shader, and then this will be the displacement pixel shader. Okay, so nothing is actually offensively wrong, so nothing's going on. So if all goes well, we should have hooked this up properly. So what we're going to do is shift this over from the normal map, and we're going to use the now available displacement map. Okay, notice that everything has gone red, and actually that has been intended, and that's because it's now one great big diffused effect. So what we're going to do is remove, let's see, I'm going to remove the specular power. I'm going to increase it, make it real big, and then I'm going to kind of like dim it down in order to dim things a little bit. All right, and now I'm going to rotate my camera just a little bit so we can actually see this. And what I'm going to do is I'm going to actually increase my displacement scale so we can actually see some of the displacement going on. Okay, gang, take a look at this. Everywhere where it's white, it's now, the vertices are now being displaced outward, and everywhere where they're black, they're more or less staying the same. And it goes in and it just pushes out like that, and you can see the displacement. And you see that once we start getting past 2, it starts to get really, really outrageous. Now notice, this is a very difficult thing, and you need to have vertex information in order to sustain this behavior. If you don't have the vertex information, let's go ahead and change our primitive up a little bit. So let's change the number of segments to maybe something like 4 by 4. Now, more or less the displacement thing goes and falls apart. And it's falling apart because there's not enough vertex information inside of the geometry in order to uphold all this data. So let's go ahead and crank this up again to something groovy, something big, 78. Yeah, that seems pretty big to me. And then we should have more than enough vertex data now in order to sustain any kind of deformation. All right, so we've got our normal map, which looks pretty good. And then we have our displacement map, which looks a little bit different, but it actually, you'll notice here that it offsets the silhouette significantly. And that's one of the big differences that we're going to be dealing with here. So what we're going to do, what I want to do now is actually go through, and I'd like to compare and contrast the two the two techniques, because we have our normal map, which is kind of good, and we have our displacement map, which offsets the silhouette, but really, what's the cost of it? So let's go ahead and I'm going to return back.